right? That's only one-dimensional data that we've been looking at so far. This always goes on autopilot. So getting to 2 dimensions. Let's just recap where we've been. We began with 0 dimensions. That's got a single y, just one number, right? And it's got identity. It's got maybe a category. Maybe it has some actual quantity, some magnitude that you want to encode and decode. And so when we talked about visualizing a single number, we talked about how that encoding might happen, and what were the various features that you might use to encode that value, and which were superior to others. So, you know, character, shape, hue, position, etc. And you've seen that the coding can sometimes be redundant, as long as it's not in conflict, because it can sometimes be redundant in any given display. And so we may want to be able to compare values and order them. And we talked about, you know, these could actually be the numbers themselves in a tabular fashion. And the tabular kind of got us a little bit going into more than one dimension. So one dimension, that's where you've got a lot of numbers that are measuring the same thing but on different units, different individuals in the population or the sample. And so each value is associated with a particular identifier. So we want you to think you've got a yi for every I. So every person here is I, and then your height is your yi, right? And we want to look at the whole collection of these individuals. That's our one dimension. We've got lots of points along a single real line. Okay, and we're trying to summarize that those patterns that we see in a way that gives us some insight into the data. So we've used a variety of things: stem and leaf, quantile function, histogram, density function, cumulative distribution function, etc. And these have different strengths and weaknesses. And I think of these, I mean, the quantile function is probably the strongest we've seen, using that in our experiments, and also what you can encode and decode from that function. So we've talked about overlaying stuff and checking things out, and in particular the quantile plot, where we looked at 2 quantile functions against each other, and sometimes they were 2 different. Sometimes it was a empirical quantile function compared to some hypothetical value, and sometimes it was like with the body temperatures of those 2 beavers, 2 different data sets comparing to one another. They had to match, something we went over quickly, didn't really mention, they have to match on the P, of course, is what you're matching these quantile functions on. And then we tried to do a bunch of comparisons and try to make a hypothesis test, try to make this formally using self-calibrating lineup tests, self-calibrating QQ plots, where we generated these envelopes and these exemplars to look at and compare, but also all of those lineup tests, right? So we've got the mechanics here of a typical statistical reasoning, right? Just it's all visual. And we're starting to get really more into 2 dimensions, because we're looking at quantile plots, it's actually 2 values. So when we're at 2 dimensions, that's the key. You've got a pair, right? So we've got for every individual, we have 2 values. So we have a pair of variates that we have some values on. Those values could be categorical, ratio scaled, whatever, same as a single number for that matter. And we talked about comparing these things. So again, looking at the 2 quantile functions just overlaid for the body temperatures of the beavers, you can see a lot of difference between these 2 things, but there's no matching here. When we went to this plot, we actually matched. That is, any one of these corresponds to a value of the body temperature on one beaver and the body temperature on another beaver. Now, I point out to you that these sample sizes were not the same, right? These sample sizes are not the same. There's no obvious matching of what You know, the 10th observation on beaver 1 should be the same as the 17th on beaver 2. No matching like that. So we had to use the quantile function itself and match on the proportion, on the p. So that's how that matching was happening. So it's kind of an artificial two-dimensional thing here. Unlike if I was looking at your height and weight, everybody would have their own pair of values, right? Okay, so that's a little different. When we looked at the cancer data, we also had kind of two values going on there. We had the survival time, and then we had which organ had the cancer, right? So we've got an X and a Y. X is kind of the organ here. So it was actually sort of like two-dimensional data there. So my claim here is that pretty much every data, geez, I even write the way I talk, pretty much every collection of data has at least two dimensions. And the two dimensions are minimally your name or the order that I have the data in. This was the guy in the first row, the second row, third row, fourth row. If I took your heights going back and forth here, they'd come to me in some order. And I'd call this gentleman the first, second, third, fourth, fifth, etc., and I look at their heights. So there's always a pair, the I and the YI. And typically it shouldn't matter. I'd be very surprised if they were all tall people at the front and short people at the back, right? We don't expect typically to be any relationship between YI and I. So we'd like to at least check that out, whether that's the case. And so we could check that immediately using a lineup test. And the lineup test would be to say, let's plot the pairs I, YI in a scatter plot. And then let's just shuffle the order and say, can you pick out the data? Okay? So here's how I do this. I'm going to use a lineup plot, so this is my display suspect. It has to have the data, which data has an X and Y. You remember before we were using that for mixing two different samples. And suspect number. So I'm going to get the order of the X's, right? And then I'm going to plot the data according to the order of the X's. So the Y is going to follow the order of the X's, okay, from smallest to largest. That's how I'm going to display things, just a plot. And I'm going to connect the dots here, so type equals B, both circles and lines between them. And my shuffle is, I'm going to sample from the X's here without sample a size that is, I'm going to sample from the X's without replacement so that I end up having a shuffle of the X's. So they're going to come in a different order. I'm going to use that. So that's shuffling X. Now I'll call the lineup with my data set that I'm going to begin with will be the one to the number of observations in the whole cancer data set, and then the survival time for cancer. Generate a suspect in this way and see whether it mattered. It shouldn't matter, right? The order that the observations were in the cancer data set. Did they come in some peculiar order? So let's look at that. So those are the plots I have. The question is, which, if any, which one of these things is not like the others? If you can't tell them apart, then it doesn't look like order mattered that much. Does any one of these seem to have a pattern? That does the Y value, does it depend upon the X value? Because when I shuffle them, there shouldn't be any pattern. Yeah? I equals 8. That's here. And the pattern is, it seems to be going up from left to right, and the others are a little more up and down. So if that's the real data, that's significance level of at most 0.05. That suggests that they actually came in some particular order. Okay? I'll leave you to do that in your head to find out what the true location is. But there's the data. And in fact, they did come in some particular order. We have them ordered by organ, and from, roughly speaking, lower survival times to higher survival times. So I suspect that 8 was this plot. And maybe that doesn't matter so much for this data set, but if your methodology was assuming that the order does not matter here, and it shows up, you're going to be caught. So you want to know whether this is the case. So it's immediately two-dimensional data, which is a nice scatter plot. Is there an order? So you always have order. Data's coming at you, whether it's streaming data or whatever, it's coming at you and you have an order. Even if it's just sitting in an Excel spreadsheet, it's got row number. Okay? So how about Beaver 1's temperature? I'm looking at Beaver 1 and I'm shuffling it. Anybody have a guess which one's the real data? It's kind of obvious, right? So definitely order matters there, the order of the observations for the beaver's temperature. They are coming in order. The temperature is going to be changing smoothly, not randomly jumping all over the place like the shuffling would suggest. Okay, so as with the body temperature of the beaver, which we know came in order and it followed that sort of smooth behavior, data often comes ordered in time. You can think about streaming data, or you can think about financial data. Lots of data or measurements here on a physical system like a beaver's body temperature are coming ordered in time. And these things are called time series, right? So you see the value over time. It's a series of observations in time. And we're going to distinguish between regular time series, where the time between each measurement is the same, versus irregular time series, where it's different. There's no regular time at which you're taking the measurements. So what happens? So even if there's time here, usually you don't expect time to matter, but I draw your attention here that you slip into two-dimensional status when time may not matter, but there's something else changing in time that's actually related to the variate that you're looking at. So this hidden variate, or sometimes called lurking variate, that it's down there, that's just is strongly correlated, or maybe are nearly identical with the time. So you'd like to observe that, figure what could that variable be. So when we actually have a time series, the interest lies in the patterns in that time series, how it changes over that time. How does that series change as time progresses? Okay? So let's give you an example. It's a very famous data set looking at sunspots. And Galileo was the first person to record observations on sunspots. And those are his actual recordings there that you see. And if you were to point a telescope at the sun and not look at it, point a telescope at the sun and imagine that the eyepiece is pointing down on the ground, you can see the sun there and you'll see little dark patches. These are sunspots. Something's happening, some activity on the sun. Okay, and so you can count the number of sunspots. So there's a modern image. And so we've observed sunspots and recorded their position and how many there are over time for some time. Okay. Right, so we have this data in R available as a time series data object called sunspots. And time series are a little richer in the sense, in terms of the data structure that's being used to encode them in R, in that they'll have start times and end times, and they'll have some periodicity, that this is going to be annual. You see, so it's going to have January, February, etc. This looks like a two-dimensional array, but it's not really. It's just a way of laying that out. It's a single time series over time. It's just we know they're going to be all January in the first column, etc. Okay, so it's a time series object. Right, so we can get the frequencies disappeared here, but the frequency is going to be 1 year 12. Right. So I'm going to look at monthly information on the sunspot activity. These measurements go from 1749 to 1983. They're collected in Zurich until 1960, then afterwards in Tokyo for this data set. And the source here that uses a book called Data by David Andrews and Agnes Hertzberg. Personal note, David Andrews was my supervisor, so that's where I know this book fairly well. They were doing it when I was a graduate student. So plot these sunspots over time. There they are. So it's a number of sunspots from 1749 up to nearly the present. You can get these more online. Question is, what do you see? What patterns, if any, do you see? You're all data viz people now. You're looking at patterns. What do you see? Well, does time matter? Yeah. It's sort of like cyclic. And what do the cycles look like? You mean that it's by cyclic you mean it's going up and down? Okay. All right. Let's look at this. Sometimes things are, I'm going to use Loon. Have we used Loon already? Yeah, okay. So here are the sunspots activity for Loon. And Loon, you can sort of zoom in and zoom out. Right, this is just scrolling. So I can make this very tiny, I can make this very large. And I can get it back to the world again here. And I can zoom in different ways. So if I zoom with the control down, I'm just zooming in that direction, right? And let's see. I can pan, move this back and forth with the right click and the control. And so you can see this pattern. You see it, notice anything about these patterns now? It's going up and down. Let's go ready, left to right. Anything in common? Anything different? Yes. Maximum height and the minimum are roughly the same no matter which one of these little waves I'm looking at. At least what? Really? Like here? It actually changes a bit, doesn't it? The minimum is you can't get below 0, so there's a boundary on the minimum. Occasionally there are very high points, occasionally the high is not. What about, does this look like it's roughly the same wavelength? These coming at waves look roughly the same wavelength. How about their shape? Anything you might say about the shape of these guys? Yeah? Steeper? Depends where I'm going. So steeper on the left and a little more graceful to grade on the right. Okay, so you can notice a lot of patterns. Can you see those patterns of that steeper on the left Lower on the right there, not so easily, right? So what am I doing here when I'm changing that? Whoa. It's just as a, okay, I'll let it swing back now. It grabs a lot there. So that's what's happening when you give it a flick. So you may not want to do that. Let me just get back to the world here. So I'm doing that scrolling, but I could also have done this to stretch it out. What am I changing here? Now you can see the whole series, or a fair bit of the series. And you can think about how often does it rise abruptly and then drop off, this sort of sawtooth. That happens fairly regularly. It's still a little hard to see. A little easier as I make this, oops, as I make this wider and wider. Anybody have a name for this that I'm doing? Anybody have a TV or computer screen? Yeah? It's the aspect ratio, right? That's what I'm changing. I'm changing the aspect ratio, this sort of the actual physical size of that vertical thing compared to the physical size of the width. Right? So the aspect ratio, you'll see different things as that aspect ratio changes. So it's really, 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 really important that you don't just plot something and look at it. You got to change the aspect ratio. You'll see different things depending upon the aspect ratio. And in fact, if I make this very small, what am I losing? I'm going to be losing that detail of what rising fast and then dropping off. Do I see anything else? Any patterns you see there? Yes? So what you're seeing is, I think this part, right? You're following that because you're crushing this together. You're starting to see this longer wavelength kind of pattern may be appearing, which would not be at all apparent when I stretched it out. Okay? Do you remember when we talked about encoding one number and what works and what doesn't work? We talked about position along a common scale. That works best, being able to tell the differences. What else did we talk about? We talked about area, length. We talked about angle. Right? Angle is not so good, not as good as position along common scale, etc. What angles are we good at telling the differences between? You don't remember? Yeah? No, not quite. We can tell if it's off 90 degrees or off 0, that's true. But telling the difference between 89 and 88 is not so easy maybe. But where do we find the easiest difference between near angles? Yeah? No, that's near 0. That's the same answer. He had small ones this way, small one that way. We can tell if they're not 0. We can tell if they're not 90 because we can tell vertical and horizontal very easily. But comparing two different angles that are near each other. Remember that stuff with the tangent? Way back when. So, I mean, actually, things near 45 degrees. We can really pick up things near 45 degrees and tell slight differences. And you'll notice that what you're, in each of these cases, you're sort of tracking the information. You're not noticing these things that are very different between 90 or not, the straight up and down. We kind of think things that are closer to that 45 degree is what you're picking up there and seeing these patterns. And when I do this, it's again, I'm able to tell subtle differences between things that are closer to 45 degrees rather, whether that's close to that, etc. So this magical 45 degrees, if you're changing the aspect ratio, you'll often see things near 45 degrees at whatever that aspect ratio is. So that's why you change it, because you're looking for different kinds of patterns. Okay? So if you compress it, the 45 degrees is going to cover a lot of time. right? So you're going to be able to see these long wave kind of things. If you're stretching it out, it's kind of like short time, you're seeing much more shorter term behavior. Okay, does that make sense? So one of the reasons we did that kind of weird stuff at the beginning is so you can now grab back and say, ah, this kind of makes sense with what we've seen from perceptual experiments. Any questions? Okay. So we can do that interactively easily with Loon, and with the zooming and panning, etc. Loon makes it very, very easy to do. We could also, of course, just change this aspect ratio programmatically. There is a argument here to the plot asp for the aspect ratio. Now you can just go through a bunch of aspect ratios and plot it, and so you can see this behavior. Again, how it becomes even easier on the left here to see this sawtooth behavior with that stretched out aspect ratio, and easier to see this kind of long wave changing with the more compressed time scale. Okay? So there's no excuse to not do this. I mean, just change this and see what patterns are presenting themselves. Okay? Any questions before we leave? We're going to continue on sunspots for a bit. So time series are such an important topic, particularly in financial matters. And what's nice about this one is it's entirely non-human. I mean, so financial series, you've got some feedback because people see a financial series and they change their behavior, and all kinds of funny things happen. The sun really doesn't care what we're doing. It's producing these sunspots, so it's a little doesn't have the feedback from us. So let's look at the sunspot again. So there's this thing called a month plot. So I'm going to show you a few plots that are kind of standard plots for looking at time series and explain what these are. So the frequency of this time series, the frequency is the number of columns it's got there, January through December. So it's got a frequency of 12 points within each year. That's fairly common, so that when the frequency of 12, a month plot is a natural thing. It's assuming you've got 12, and we'll look at month plot of these sunspots, and that's what a month plot looks like. And you can question how valuable that is, right? What's it showing? Well, it's showing the time series over all of those couple of centuries, two and a bit centuries, and it's showing it for every month. So there's the time series for January, there's the time series for February, etc. So you're getting to see, is this pattern, this compressed aspect ratio pattern, so the long range behavior, is it the same for each one of these months? And in the middle here you see a horizontal line, and these are the averages, which if this were changing over the year, you may see this going up and down, but sunspots don't really care about the year. That's an Earth thing. That's a terrestrial thing, the year. Sun doesn't care how frequently we go around it to produce the sunspots. Okay, so there's not much happening there. So you could try changing the aspect ratio with that. Here's another one that's quarterly now, just by doing a little bit of modular arithmetic here. I look at the quarters, so the first quarter, second quarter, third quarter, fourth quarter. Rather than months, I've got quarters. But it's still a month plot. Okay? All it means is by that frequency that you're using. So this is giving it the phase of which months are in that quarter. So again, they look kind of the same over each quarter, but it's kind of hard to tell like that. What you might do is, of course, plot these on top of each other. And so here's a quick and dirty thing of plotting one on top of the other. So I'll plot the sunspots for 1 year, and then for all years, a single month, and then I'll add each month on top of that. So that's why it's going for the first month, and then 2 to 12 are the other months. And we get something that looks like that. So now that's the time series, 12 different time series plotted on top of each other, different colors, and you can see the agreement, okay, over time. So the months all seem to be about the same there. So lots of ways of looking at this. So let's see. I'm not going to get through this, I think, but let's start this. So another way of looking at this is a lag plot. And let me just say what a lag plot would be. Since I'm not going to get through this, I'll tell you about it. So I've got values y at time t. And I say, well, what does this look like compared to some time ago? A lag, right? So I might look at yt on the vertical axis, and then compare that to the value k time periods ago. There's all regular, assumes we've got a regularly spaced time series, right? So this is, if this is t and k is 12, this is the previous year value. If this is 1, if k equals 1, it's the previous month for this data. So this is a lag of size k. And so I could plot these pairs for all t, right? Fix k for all t. And then I get to see, does it look like the sunspot activity in any given month looks a lot like the sunspot activity in the previous month? Does it look like that? If it was lag 1. So that's lag 1, and the scatter plot, we'll just end with this, but the scatter plot looks like that. And sure enough, it looks like there's a relationship. It's correlated at least, right? Fairly strongly correlated. That if you saw this many sunspots last month, you're not going to see two different, right? Unless, of course, there's a large number of sunspots. It does seem like there's greater variation out here. If I'm seeing 150 sunspots, I could see anywhere from 50 to 250. Less so here. If I didn't see any sunspots last month, I'm not going to see too many next month. So it's not perfectly straight line. Maybe it's fanning out a little bit, but it's definitely a correlation. So that's a handy plot, just looking at what did it look like in the immediate past or some period in the past. And it depends on it being regular time series, regular spaces between the time intervals. Okay? Okay, so we look at lags here for any number of time periods back, here 1 to 12 months. So if you look at that, the first plot is lag 1. So this is the number of sunspots in that particular month versus the number of spots in the prior month. Now it's number of spots in that month versus 2 months ago. Number of spots versus 3 months ago. 4, 5, 6, 7, 8, 9, down to 1 year ago, 12 months ago. And you might notice that there's the lag is still giving you some idea of how to predict how many sunspots there are in a given month based on on the number of sunspots some number of months ago. But you'll also notice that it's tightest here 1 month ago, and it seems to getting more dispersed the farther back in time. So it's not doing quite as good a job at being able to predict that. Does everybody see that? Okay. So we could go back farther. We could lag by years just by multiplying this frequency here. So 12 times 1 to 15, go up to 15 years ago. And we see the following patterns. So this would be lag 1 year, so 12 months ago, 24 months ago, 36 months ago, 48 months ago, 1 year, 2 year, 3 year, 4, 5, 6, 7, 8, etc., up to 15 years ago. Any comments? What do you see now? Yes? Right, so it still seems to be tightest here, right? 1 year ago, it's not as tight as it is a month prior, but it's still tighter than as we get here 3 years ago, 4 years ago, and down here 15 years ago. It doesn't look like there's much of a correlation there at all. Okay, so it's degenerating over time. Anything else you might see? Have a look at the plots. Yes? The third row of plots, yes? So it's kind of crummy here in the second row, and then it starts to get better again, is what you're saying? It sort of gets a little tighter. Yeah, that seems to be the case. Everybody see that? And then it falls apart again. So 8, 9, 10, 11, 12. So, 10, 11 years ago, it seems to be a little tighter. Right? So we could, in fact, because the data are non-negative and seem skewed, they've got a long right tail, I could maybe try square roots of these counts, see if we pick up anything better. So to get rid of that heteroscedasticity, so to speak. So now look at these lag up to 15 years. 1 year, pretty good now, sort of nice relationship. And again, falls apart. In fact, seems to go negative the other direction, right, at some point. So 1 year goes good, 2, 3, 4, we're starting to be that actually there's a relationship again, but it's in the other direction. And that seems to be going again here at 5 years, a negative, that low values 5 years ago seem to be associated with high values now. And that goes on, and then it falls apart again. And now around here at 11 years ago, we're seeing that positive relationship again. Everybody see that? So that's suggesting some kind of pattern, isn't it? Sorry? It's a cyclical pattern, just seems to be going on there. What's the length of the cycle? Well, when do you get back to again, you seem to be getting back to this positive relation sometime around here, 10, 11 years. Right? So, is there a possible 11-year cycle? So we might look at just looking at monthly differences, zooming in around 11 years. So I'm looking at square root of the sunspot counts, lagged 120 to 144 months. 132 months is 11 years. So 132 is around here. And again, you are seeing this tight coupling here, this tight correlation around 132, and it's kind of tight on the other side, and it's getting tighter as we get closer to 132 and then falling off again as we get farther away. So maybe there is an 11-year cycle. Whatever the sun's up to, it's doing it on 11 years. Okay, in its activity. So just to pull back a bit now, all I'm doing is changing these lags to look at every 4 months. So again, 132 of the 11 years right in the center there. And you can see that pattern. We've got the tightest correlation around 11 years here, 4 months on either side. Okay? So just using these these lag plots, looking at what's happened now versus what happened some time period ago with these nice regularly spaced series, we can start to see some patterns. Okay, which suggests something that may be happening physically underlying the phenomenon of sunspots. Okay. Do point out that an 11-year cycle is, again, pretty suspect because the sun doesn't know about years. Years are just how many times, it's a measure of how long it takes for us to orbit the sun. So one doesn't imagine that has anything to do with the solar activity. So the 11 years, maybe it's not quite 11 years. It'd be really surprising if that was on 11 years, that there'd be any connection, tightly coupled. but it could be 11 point something or other, or 10 point something or other years. So something that's near 11 years that we've seemed to have uncovered. Right, so looking at the square root of the sunspots, we discovered an approximate 11-year cycle by looking at these lag plots. You might want to think of other ways to investigate that possibility of the 11-year cycle. And one way is to just take every 11-year cycle and distinguish it visually in the display. So to do that, I need to identify all of the cycles, and that's what this is about here, is just creating a time series. It's going to be our square root of the sunspots. So we're working with the square root of the number of sunspots. And then producing the start years by just marching through this time series, just picking off cycles of a length 11. So the first cycle goes 1749 to 1759, 1760 to 1770, etc. So each cycle has 11 years in it. And these are the beginnings of each cycle. So now I have to do colors. I can just use 6 different colors, rainbow with some opacity of about 50%, just so I can see some transparency there. And I want to have just 6 different colors, but I want to have as many colors as I have cycles. What I'm going to do is repeat the numbers, the month numbers, 1 to 132, that's how many months there are in 11 years, and repeat that for every number of cycles. Okay, so for that many cycles. Right, and finally, you can see that each cycle has a unique number. So that done, I can color them. So here we see from this plot now of all of things, every 11 years is given a different color: red, yellow, green, blue, light blue, blue, violet, red, yellow, just repeating the rainbow. And if you look at this plot, you can see that there is sort of the cycle pattern is picked out. Every cycle appears to be roughly a V. Right? So you see the red V is everywhere, and most of the times it is just picking a good V for that cycle. So it does seem to capture this 11 years, seem to capture the cycles pretty well. But there are exceptions. So you look down here in these early years, this green to blue, the green goes over into the next one, which causes the light blue to go over to the next one. And so there's a little bit of misalignment here in the cycle. So these are not quite 11 years, these early ones, without the green one at least. And then we can also see a bit of misalignment over here later on between the purple and the red. So they're not quite perfect, but they're overall fairly well, with some odd exceptions where things just are not working very well. Okay, so that's somewhat reassuring that we've identified the cycles, at least that we see in the series. That 11 years seems to be close to the right value. So just as we did with when we looked at the months, right? Looked at all the Januaries for the cycle and all of the Februaries and plotted them on top of one another. We might do the same thing now for these cycles to see whether or not they align, just like those other cycles. Just as the time series aligned for each month. The January time series seemed to be right on top of the February time series, right on top of the March time series, etc. But now we're just going to look for the cycles. So I'm going to plot the first cycle only, right? So I just want to get where I'm going to start and end. I've got a window for this data, start and end at some place from the first of the start years to the second start year, back one for the end here, okay? So if I plot that, I have the first sequence. So the first sequence, that red one from 1749 to 1759, month numbers from 1 to 132. We see the pattern. This is the kind of V that we had. We see a lot more detail here because we've stretched it out. But that's our V pattern that we saw in the other plot of the whole time series where it colored the cycles. If I overplot this now, I want to say I've got that first year. Now I'd like to plot on top of that the remaining cycles. Okay, just plot them right on top of that, months 1 to 132, and just see whether those cycles seem to line up when I have them on top of one another. Colors will be exactly as they were before. So instead of having them end to end, it's as if I wrapped them around and restarted them every 11 years at the start again. Here's what it looks like. So for the most part, you do see that kind of V that they're lining up. There's a lot more detail here, so it's of course they're not perfectly matching each other. There's a lot of variation. But you do see that rough V there. There are some exceptions here that really pop out now. They maybe pop out a little more substantially here than they did on the graph of the time series where the cycles are laid side by side, just connected in the full time series. You see these two series pop out. So there's some evidence of 11-year cycle and that the valleys and peaks are roughly the same place, but there are noticeable exceptions. These may be due to that misalignment we saw before, and some of these other are a little bit off alignment. There's one series that has a long bunch of zeros in sunspot activity. Okay, so there might have to be some refinement of the 11-year cycle. What makes this a little bit fun if we actually do a look at this interactively, this time series, which we can do with the Loon package. And here we'll plot the time series as before and overplot all the cycles on top of each other. Now instead of lines, I'm going to have characters, so you'll actually see the scatter plot, as it were. And have a histogram. The histogram is going to identify the cycle numbers. And these things are all going to be linked. So you see linking group of sunspots in each one of these graphics. So that'll mean that we'll be able to brush and connect these various displays. And adding lines on top of them, I'm going to add the lines with layering a line, etc. Okay. So let me have a go at that. So here's going to be Loon. This is just the code that we just looked at. And let me do this first with before the lines are added. And move this in. So there are my sunspot cycles. This is my data. There's the whole cycle where I have the colors side by side. So I can see the cycles, roughly those V's we saw before. Again with the misalignments. I can see which cycle is which. Here with this histogram bar plot, which I select, I can pick up any cycle and see where it appears in the other plots. And then this is the overlaid cycles themselves. You see that roughly that V pattern that we have. No lines connecting it. But I can also see that the greens here, these odd ones up here, those two different series, and you can see them over here, those early cycles. So I can select them, the entire cycle here, and this one as well, and maybe make those all a little bit bigger. Click on the scatter plot here and make them bigger. We can actually identify and see how strange they look. Might also just change their shape in both plots here. So those are definitely the strange ones, these little triangles. And that's the green series, which is appearing early in time here, and the pink series also appearing early in time when we saw that misalignment. So the misalignment here in the whole time series and the misalignment when I wrap the time series, restarting every 11-year cycle, it becomes kind of obvious. Just for the heck of it, let's add on these layers of lines. So now, a little more complicated. You see that the graph looks a lot more than we saw before. We've got lines showing, connecting the dots, so you can see what is in one series, what's in it. We can, of course, take those away. Right, so you can see that these outlying sequences here are the strange ones where there's a misalignment, and that's what's happening. If we move this over a bit, we wouldn't be able to find it. In fact,
places there where it's misaligned, for this group right here, right? And I looked at just this group alone, this V, here, that thing, there's the V. Somehow that's the cycle that we should be looking at. This is part of the next cycle. So we've got these cycles misaligned because they're not exactly 11 year, at least not in this data set. These early measurements don't seem to be the 11-year cycle. Whether that's something strange happening in the sun at that time or something really recording of the data around this time, that would need to be investigated. Okay, that's it for sunspots for now.